So what we'll do today is basically go over a little bit of an overview of plates and shells. It's obviously a very big topic, and it's not really possible to do it in a couple of lectures, but hopefully I'll try to give you some sort of an overview so that later on if you look at it again, you have some idea of what the theory means and how this works. So are there any questions before we begin? How many of you have finished your project? Okay. um, so yeah, what I'll do is I'll set up a online submission for your PDF file for the project and a CAE file for the project. And also, I think those of you who haven't filled out the course survey, please do that and leave plenty of comments for me. And also, this coming Wednesday, just to let you know, there is a Midwest Mechanics seminar. So this is for those of you who might be interested in mechanics topics. This is a seminar that is organized by all these institutes put together, but unfortunately this seminar is at the class time. So Wednesday 1:30 in ME 256. So I think it'll be better if we call the class off on Wednesday and you all can attend the seminar instead. And what we'll do today is I'll try to finish out this topic on just give you an overview of plates and shells, and if anything is remaining, then we can come back on Friday, and that'll be the last lecture. Okay. So, sorry. So the seminar is being given by Professor Will Curtin from Brown University. And those of you who don't know, Brown University has been has a very strong mechanics program, and he's going to talk about some multi-scale methods for plasticity, so metal material properties. And I'll send you the announcement. I'll forward you all the announcement so you can attend that. All right. So no questions from beams and frames. Has anybody tried using beams and frames in Abacus? Okay. But yeah, so you can try it and see how things work in the case of beams and frames. So what we'll do today is this topic on plates and shells. So just like beam theory, plates and shells are also structural theories. And what that means is that we will assume a certain type of deformation. So for example, if you have a plate that is constrained on the corners, or a structure which has one dimension which is much smaller than the other two, those kinds of structures, they can be treated as plates. In general, you can also have curved surfaces, and the mechanism that these curved surfaces use to resist loads is a little different than plates. You can imagine if there is a vertical load acting on this plate, the primary mode of load resistance is going to be bending. As opposed to plates, in shells what happens is the primary mode of load resistance also has an axial component. So you can imagine if you have a lot of vertical load here, a lot of in-plane action would also come into being for the shell theory. So what we'll do here is try to draw parallels from our beam theory. And if you remember, in our beam theory, what we said was that a beam is a structure which has one dimension much longer than the other two. And we treated a cross-section as a rigid cross-section. So a very similar thing happens in terms of plates. What we say is, let's say you have this type of a plate. It has a thickness h, and we will consider the centroid or the centroidal surface of this plate, and we are going to consider these small needle-like things that stick out from the centroidal surface. And just like in the beam theory, we assume that the cross-section remains rigid. In plate theory and in shells, we assume that the deformation is going to be completely, will make sure that this needle-like object remains rigid. So you can imagine that if you have a plate, at least theoretically, the way to see this geometrical object is that you have a surface and there are lots and lots of needles sticking out of it. And these are rigid needles. So when you deform the plate, those needles are pretty much constrained at the centroidal surface, but they can rotate a little bit. They can rotate about x1 and x2 axis. So that's what I'm showing here. You consider this this small portion of this plate right here, and if there is a point P that is on this needle, then the deformation map says that this point O is going to translate to this point O prime. So if you give me a location xy of this centroid, I immediately know where this centroid went. So that this displacement W, this is a vector which is a function of only x1 and x2. So x1 and x2 are the plane of the plate, and x3 is the vertical dimension. Since as soon as we find the centroidal location, after that what we'll do is we'll rotate this rigid line by a small angle θ1 and θ2, which are our rotation components along x1 and x2. So θ1 and θ2 are small rotations. And for small rotations, what you can do is you can write out all the coordinates for these points. So for example, the coordinates of point O, they are x1 and x2. Coordinates of point P, they are same x1 and x2, which is O plus this small distance x3 right here. So for the coordinates of point O prime, we have O plus this W displacement, and similarly for P prime, we have O prime plus theta cross this small vector. So theta cross this small vector pretty much takes that needle and rotates it by a little bit. So this is the kinematic assumption that is very similar to what we had for beams. In beams, we said that we have a centroidal axis. We will take a point on the centroidal axis, transform it to a new, or translate it to a new place, and the cross section is going to go there and rotate whichever way it wants. That was beam theory. In this case, we have a plate, and there's a needle sticking out. When it deforms, the plate goes to a new position, and this needle can also independently rotate. Okay, so the general deformation, as soon as you give me the location of a point x1, x2, x3, I can tell you where it went in the deformed configuration. So this is the kinematic assumption, and this is common to all types of structural theories. Once again, the idea behind doing this kinematic assumption is that we do not want to simulate, or we do not want to analyze this entire plate as a three-dimensional object, because you know that unless there are like 4 to 8 elements through the thickness, we are not going to get good results. Even for a simple cantilever beam, you remember we needed 4 layers of elements at least to get a good displacement. So so the idea is that people found that we can express the displacement of the entire plate through the displacement of this centroid axis and the rotation of this fiber. So given this kinematic assumption, we are going to define what are called stress resultants. Now these are very similar to our beam stress resultants. In beam theory, what we said was we have a shear force, Q. So let's just consider a planar beam in the x1, x3 direction. So this Q is nothing but the shear force, and it's a function of x. And the way we obtain shear force is by integrating the traction on this cross section. You go to any location x, you obtain the traction and integrate it over the area of the cross section. That's the shear force. Similarly, you have bending moment. If it is a x1, x3 plane, then the bending moment we are concerned about is this M2. Okay. And in both these cases, the shear force and the bending moment is a function of the coordinate along the x. So the similar idea holds for plates. What we have here is a small infinitesimal plate element. And what I'm denoting here is the stress resultants for the plates. Just like the beam theory, you have Q1, we have a Q1 and Q2 in this plate element also. So these are out of plane shear forces which are acting on, this is the x1, positive x1 phase, and the Q1 is acting in the 3 direction. Similarly, out of plane Q2 is perpendicular to the x2 phase. We also have in-plane forces. In-plane forces are N11, N12 on the first phase, N21 and N22 on the second phase. So these are your your shear force and in-plane force resultants. And the way to calculate them is, instead of integrating over the area of the cross section, here we are going to integrate it over the length of this needle. So if we just take the traction at any point, integrate it through the thickness of this plate, we will obtain a stress resultant. The stress resultant has axial forces and shear forces. So similarly, you have bending moments. These bending moments are obtained by taking the cross product of E3 with the traction. So what happens is, these are bending moments which are very similar to our beam bending moments, but again we have 4 components. So why don't we have a bending moment in the 3 direction? If we take a look at the expression, the way we are calculating bending moment, we have E3 cross T alpha. So any component, when we cross it with E3, it cannot lead to a bending moment in the 3 direction. So that's why we do not have any bending moment in the 3 direction on either x1 phase or x2 phase. So once again, what we do here to calculate the bending moment is that we integrate the moment of this traction across the centroidal face. So what this is doing is, just like the bending moment is a function of x along the length of the beam, this bending moment for the plate is a function of x and y. This is a location within the plate. And similarly to the shear resultants and the bending moment, they are both a function of x and y. So in general, these are the stress resultants for a plate theory. And these are basic things that you have to keep in mind when you're dealing with plates, about these resultants. So what we'll do is, now that we have a kinematic assumption and we have our shear force and bending moments for the plates, we'll try to write the equilibrium equations for plates. And the way that turns out is like this. What we've done is we have simplified our plate to just the centroidal surface and one needle. And when we want to say, or when we want to write an equilibrium equation for a general point xy, anywhere in this plate, for a general point xy, if you write out the sum of forces by just integrating our equilibrium equation, this was our equilibrium equation div sigma plus b. You integrate that equation over the length of this needle, you are going to get this governing differential equation. And this is also very similar to div of sigma plus b. This is a derivative of the shear forces plus the applied load q is equal to 0. Similarly, if you write out sum of moments is equal to 0 and just integrate it over the length of this fiber, what you get is this derivative of bending moments plus shear force plus applied moments is equal to 0. Do you, hopefully you remember a very similar form for the beams. Let me actually go back and show you that right here. So this was the bending moment, or this was the equilibrium force equilibrium for beams. Derivative of shear forces plus applied load is equal to 0. Derivative of moments plus E3 cross the shear force plus applied moments is equal to 0. So even for plates, we have two very similar equations. And here, alpha is an index which is denoting the resultant, like alpha could be 1 or 2. So it's we have to follow the initial notation here, meaning you have to sum it over alpha is equal to 1 and alpha is equal to 2. So if you write out all these equilibrium equations in terms of the stress resultants, just expanding it out, the in-plane forces can be written out like this. So these were the N11, N12. This is for a very small infinitesimal plate element. If you write out the derivative of N11 plus N12 with respect to 1, plus the force, any applied force in the one direction, that has to be 0. That's the in-plane force equilibrium. Similarly, in the two direction, you have in-plane force equilibrium, and this is nothing but a very similar equation to what we have when we say shear forces N12 and N21 have to be equal. Shear stresses have to be equal. So the corresponding equation that we get for shear stresses is for these shear resultants. Similarly, for the transverse and bending equation, we have this equation in the third direction, that is saying that the shear force, rate of change of shear force in the one direction, plus rate of change of shear force in the two direction, plus applied load in the three direction have to be 0, and the two moment equilibrium equations. So these equations put together, these three and these three, 6 equations of force equilibrium and moment equilibrium for any small infinitesimal plate element. So another thing to note here is that even though we have 6 equations, only 5 of them are actually differential equations. So these 2 and these 3 are differential equations of first order, which means that we will need at least 5 boundary conditions. Okay. So now that we have equilibrium equations, some of the strain resultants, you can also use the same kinematic assumption that says that the centroid will go by W and this fiber will rotate by theta 1 and theta 2. So one another thing to note here is that the theta 3 component of this rotation is 0, because if this is the fiber, if you twist it along its axis, there is no change in the position of P. Okay, so the theta, the rotation of that fiber has only 2 components, theta 1 and theta 2. So you can define these strains, axial strains and curvatures. In beam theory, if you remember, we said that the curvature was theta prime. And in plate theory, we have theta comma alpha, which means d of this theta vector taken with respect to E1 and E2. Those are the curvatures, and actually these should be vectors. This curvature is a vector, This theta is a vector. This theta is a vector. Um, and if you just write out the curvatures or the strains and the curvatures, you can actually see the physical meaning of this also. So E11 is the strain, or E1 is the strain in the one direction. This is omega 1, this is the displacement with respect in the one direction with respect to 1. So you can imagine that is the extension in this direction. This term W1 comma 1, that is the extension in this direction. W2 comma 1, that is the shear strain in this direction. W3 comma 1, that is the shear strain right here. So this W3 comma 1 measures the rotation uh, of this centroidal axis. And plus theta 2, that is the amount of shear. So just like the beam theory, we have W3 comma 1 plus theta 2 is the total amount of shear. This is gamma. And similarly here, gamma is W3 comma 2 minus theta 1. And here gamma is W3 comma 1 plus theta 2. So you have to be a little bit, you have to think in a little bit of a 3D way that this line is going to rotate with respect to x1 and x2 with angles theta 1 and theta 2. So so the angles that it makes with the when you rotate it about theta 2 here, that's the angle that it makes with the x3 axis. So all these quantities have a clear physical interpretation in this case. And similarly, the curvatures also. The rate of change of rotation, theta 1, as you pull it out in the one direction, that is going to be a torsional mode for the plate. Similarly, theta 2 cross theta 2, that is going to be a torsional mode for the plate in the two direction. So this is all a little bit of a theoretical development here, but it's important for you to realize at least these strain or these stress resultants and what are these strain, what are the corresponding strain resultants. Because all our weak form, all the finite element formulation is based on all these quantities Q, N, M, and these strains and curvatures. So another important thing here for plates is the distinction between this thin versus thick plates. So just like in the beams, we had a Timoshenko beam. Does Timoshenko beam allow shear? Or okay, so Timoshenko beam allows shear, and Bernoulli-Euler beam assumes that the beam is rigid in shear. So the very similar analogous thing happens here. Thick plates, where the thickness of the plate is comparable to the dimension of the plate, in those types of situations, the shear deformation is important. So you can imagine if these are the two adjacent faces of a plate, if you have this type of a variation or this type of a deformation, that's a shear mode. If you have this type of a deformation, that's a bending mode. Okay. So similarly for thin plates, where the dimension is very small compared to the longitudinal dimension, in that case, the behavior of this plate is predominantly in the bending mode. We cannot actually say that 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 shear is going to be 0 in reality, because there is always shear even for thin beams. But that amount of shear is pretty much negligible. So this type of theory, where we say that the shear is negligible, is called the Kirchhoff-Love plate theory. And this thick plate theory is the Reissner-Mindlin plate theory. This is similar to Timoshenko beam. This is similar to Bernoulli-Euler beam. Um, so another consequence of using this thin plate theory is that the shear strains vanish, meaning that this needle is always going to be perpendicular to the centroidal surface. So if you remember for the beams, in the beams we said that, let's say this is the cross section and this is the centroidal line. If we shear them, then this centroidal line may not be normal to the axis of the beam. Similar thing happens here. Uh, if this if this is the centroidal surface and this is the needle, if we assume that shear strains are going to be zero, then this needle always remains perpendicular to to this centroidal surface. So in this case, you can see that the initially a needle that is perpendicular to the centroidal surface need not be perpendicular when there is shear deformation. But when there is no shear deformation, the needle that is normal to the surface remains normal to the surface. Um, so after making this distinction, there are a bunch of material constitutive relationships. And if you want to know more details about this, you can take a look at the references that I've mentioned. I think on the very first page there are the material that I've drawn from is from the Jumstad's book, Chapter 8, and Reddy, your textbook by Reddy in Chapter 12. Zienkiewicz and Taylor, Volume 2, also has this Chapter 11 and 12 on plate theory. So in case you are interested or want to know more details, these would be some of the sources to start looking for things. So the material constitutive equations for the in-plane forces, we are trying to express all the in-plane forces in terms of displacements. W1, W2, all the W are the displacements. Similarly, out of plane shear, those are Q1 and Q2. And if you should maybe go back to the previous page and take a look at what these N1, N2, and all these things are. What are these Q1s? So once again, these are in-plane forces. These are out-of-plane shears. And for the Reissner-Mindlin theory, since that is not rigid, that is shear deformable, therefore we have a constitutive equation. We have a material law for that shear deformation. On the other hand, the Kirchhoff-Love theory, we assume that the shear is rigid. So we cannot have a material law for something that is rigid. If this is rigid, no matter how much force I apply to it, it's not going to deform. So we cannot find out the force acting within a rigid body from material laws. What we have to use is equilibrium. So if these two relationships are the equilibrium relationships, very similar to the Bernoulli-Euler beam that we used to calculate shear forces. And similarly, you have the relationship between moments and curvatures. So just like in the beam theory, we had m is equal to ei theta prime or ei w double prime. Those were the curvatures. Here we have bending moment is related to curvature, and all these theta derivatives are curvatures. So again, this note that these alpha, beta, and all these things are Greek indices which go from 1 to 2, not from 1 to 3. And this E gamma beta or E alpha eta, this is a permutation symbol that is used to just express all the 4 constitutive equations all in one. So I'm not going to expect that you can understand this right away, but if you take a look at this, hopefully you should be able to work out the algebra and see what's going on here. So once we have the equilibrium equations, when we have material constitutive laws, the last thing that we need is boundary conditions for the Reissner-Mindlin plates to complete the problem. Just like in the 3-dimensional or the 2-dimensional case, we had equilibrium equation, material properties, strain displacement relationships, and boundary conditions. So this is boundary conditions for plates. So one type of common boundary condition that you might see for a plate is a fixed boundary condition. We say that along this edge, the centroidal axis, all the displacement components have to be 0 along this edge. And not only that, the rotation at this edge, so you can imagine, let's say you have a plate, this is a plate, and this is the needle that is on the fixed edge. So this is the fixed edge, and this is the needle here. If I say that W is 0, that does not say anything about this needle. The needle is still free to rotate. So in addition to fixing the plate on this edge, we need to say that this needle cannot rotate. So rotation perpendicular to the edge is 0. Rotation in the plane of the edge is 0. So that's those two conditions. Theta dot n, that's the rotation in the plane of the edge. Theta dot s, s is this vector along the edge, that's rotation like this. So once we have these equations, then we can say that we have a complete set of boundary conditions on this edge. So how many boundary conditions are here? We have 3 boundary conditions for W, which says that all the 3 components of the displacement of the centroid have to be 0. 3 boundary conditions right here. We have 1 boundary condition here because this is a scalar, theta dot with n and theta dot with s. N is the normal vector to the face, s is the tangent vector to the face. So 2 more boundary conditions, 5 total boundary conditions on each edge for Reissner-Mindlin plates. So this is consistent with what we had done for the equilibrium equations. We had 5 equations which had derivatives, so we have 5 boundary conditions. Similarly, we have a free edge boundary condition. This pretty much says that the shear force or this Q alpha actually includes all the in-plane forces and the out-of-plane shear force dotted with this normal vector have to be 0. So shear on this face has to be 0. That's the free end for the beam. Similarly, moments on this free edge have to be 0. That's a simple free condition. A simply supported condition where we say that the displacement all along this edge has to be 0, but the rotation. So a simply supported beam, simply supported plate cannot have the fiber rotating like this, but the fiber can rotate like this. So that's why we have this one condition which says that the fiber cannot rotate in the S direction, but it can rotate in the normal direction for the simply supported case. So once again, we have 5 boundary conditions here, 5 boundary conditions here. And the reason we have 5 boundary conditions here is because the third component of M, it's 0. We have 3 equations here, and we have 2 equations here. If you remember our moment resultants don't have anything in the 3 direction. So so this one has 2 equations, this one has 3 equations, 5 equations here, 5 equations here, and these are the types of boundary conditions that Reissner-Mindlin plates, thick plates have. So after that, all that we do is something very familiar. We will take our equilibrium equations. This is the equilibrium for in-plane shears and moments. Multiply them with virtual displacement, virtual rotation, integrate by parts, and what we end up with is our weak form. So take the equilibrium equation, multiply it with virtual displacements and rotations, integrate by parts, and you will get your weak form. Here all the derivatives are pretty much balanced. there is a derivative with respect to displacement in here, and there's a derivative with respect to displacement here. So um, what we can do now is, so this type of a thing is valid for the entire plate. At every point, we have integrated over the domain of this plate. So when it comes turn to do the finite element approximation for this, what we'll do is we'll treat this as a two-dimensional object, and we'll just divide it up into triangles or quadrilaterals or whichever types of elements you want. Um, so another thing to note here is that when you are dealing with thick plates, the highest order derivative in this weak form is 1. In this E alpha, if you go back and take a look at all these strain resultants, E alpha and curvatures kappa alpha, they have derivatives with respect to alpha. Only one derivative, W comma alpha, theta comma alpha. So the highest order derivative, is 1 in this weak form, and therefore what that means is we can choose shape functions which have square integrable derivatives, meaning that all the two-dimensional finite elements, the T3 triangle, Q4 element, T6, Q9, and all those things that we had developed, they are valid choices for uh, for the Reissner-Mindlin plate element. But you have to keep in mind that at each node, you will have these 3 displacement degrees of freedom and 2 rotational degrees of freedom. So each node will have 5 degrees of freedom for a plate uh, element. Um, but just like the Timoshenko beam element, if you use equal order interpolation for W and theta, meaning let's say if you choose the 3 nodes to interpolate W and you choose the same 3 nodes to interpolate theta, what you will see is that the phenomena called shear locking. For very thin plates, once again the shear is proportional to W prime and theta. So if you choose equal order interpolation for these W and theta, that leads to shear locking. And just like we solved the shear locking problem in Timoshenko beams, we'll use reduced integration to integrate the shear term. So the shear term is right here. This term is the shear term, and this term is the bending term. These are all applied forces. These are all applied forces on the boundary. So if you integrate the shear terms with a lower order quadrature with reduced integration, then that solves the problem of shear locking for plate elements. Um, so you can see that for this Reissner-Mindlin plate theory, since all the derivatives are only of the first order, things do not get that complicated. But on the other hand, if you choose the Kirchhoff-Love plate theory, then things become very complicated very quickly. And let's take a look at that. So the assumption that the Kirchhoff-Love theory uh, makes is that the shear strains are going to be 0. So the shear strains for the plates, they are these 2 shear strains. And if you set them to be equal to 0 and further make some assumptions, let's say we are going to consider only the bending problem here. So let's assume that there is no, or we are not concerned about the displacement 1 and 2 right now. We'll just consider displacement in the 3 direction. So that's the transverse displacement of a plate, W. And let's say that the load, applied load, is also purely vertical. There is no applied load in the 1 and 2 directions. And let's say there is no applied moment. So under all these assumptions, we can modify the moment curvature relationships. So once again, you can see that the moment is related to the second derivative of W. But in this case, the second derivative has, you need to take differentiation with respect to 1 and 2 directions both. So these are moment curvature relationships for plates. Um, and if you take all these assumptions and plug them back into equilibrium of moments, you get a very nice, simple equation that governs the behavior of plates. Here, D is the plate modulus, just like EI was our beam modulus. This D is the plate modulus that is given by E h cube over 12 over 1 minus Poisson ratio square, where h is the thickness of the plate. And this fourth order derivative that is defined right here. So this W is a scalar. You take the fourth derivative with respect to x, mixed derivative with respect to x and y, and fourth derivative with respect to y, sum that up, and this is the governing equation for Kirchhoff-Love plate equations. So now boundary conditions for Kirchhoff-Love plate, they are similar to Reissner-Mindlin except for the free boundary. So let's first take a look at the fixed boundary. Since we are dealing with only a scalar, we have this equation that says on this edge W is fixed. So W is 0 on this edge. In addition, we are saying that the derivative of W, the gradient of W should not change in the n direction. That's the fixed plate boundary condition. And before I go to free, let's talk about the simply supported, which is also the same. W is equal to 0 all along this edge. And the moment, applied moment on the n face in the s direction. So this is the applied moment on the normal face in the s direction. That has to be 0. And the free face boundary condition is actually a little bit tricky. It so turns out that when you write out the weak form for this free boundary condition, the derivative the derivative of W with respect to the free face in the normal direction is not independent. So I'm not going to go through the derivation of this, but this is something that you need to keep in mind, that for Kirchhoff-Love plates, there is something called effective shear boundary condition. Normally on a free surface, we say that shear is 0, moment is 0. But for Kirchhoff-Love plates, on a free edge, you cannot say directly that the shear is 0. What is 0 is something called effective shear. And this is the Kirchhoff free edge boundary condition. So once you have the boundary conditions and the governing equation, you can again go back and set up the virtual work weak form. Take our equilibrium equation, multiply it with virtual displacement, integrate by parts twice because you have fourth order derivatives. So once you do the integration by parts twice, you get this equation. Here you can see that the derivatives are balanced between the virtual displacement and the real displacement. Virtual displacement and real displacement. And these are the applied loads. So you can immediately see that for this weak form, the highest order derivatives is 2. And that creates a lot of problem. So what that first of all means is that any approximation function, if we were to choose Ritz basis or if we were to choose finite element shape functions, those shape functions have to be, you have to be able to take the second derivative of those shape functions and they have to be square integrable. Meaning, if you were to discretize this plate with finite elements like this and consider this node. So the shape function for this node from our two-dimensional finite elements would be something like this, a tent shape function. But we know that these tent shape functions, they have this sharp edge between the adjacent faces. And this sharp edge means that the second derivative is going to be discontinuous. The first derivative is discontinuous. The second derivative doesn't even exist. So these types of shape functions are not admissible shape functions for the Kirchhoff-Love plate. Um, so, and you can also show actually that if you have these 3-noded triangles or 4-noded quadrilaterals, and if you choose only 3 degrees of freedom per node for only for the bending, there are obviously W1 and W2 degrees of freedom also. But let's say if you choose only 3 degrees of freedom for the bending directions, then it is not possible to enforce compatibility between these two faces. So what people do sometimes uh, is construct higher order elements which have additional degrees of freedom at the nodes. But there are also a lot of elements that use this incompatible elements. So we immediately know that these 3-noded triangles, they are incompatible on the edge. But even then, a lot of people use these 3-noded elements, knowing that it is not correct. But even then, sometimes we get good results. Um, in general, to construct a compatible element, you would have to include higher order terms like this. So each node would have degrees of freedom for W, the 2 rotations, and the bending directions. And actually, there's a lot of literature on these types of shell elements, and there's a lot of research also going on right now to construct these types of elements, which would have derivatives that are continuous along these edges. And it is not trivial to actually construct these derivatives, especially when you have isoparametric map. So you can imagine there's a parent element, you have to map it to an actual element, and in the actual element, your derivatives must match. So, so this remains an active area of research. But let me just give you a small abacus example for a simply supported plate. Um, so this is a simply supported plate. You can create this part very easily. If you just go deformable, shell, and of type extrusion, and let's say if I just make this line here and say done, let's say if I now if I say extrude it, then it will let me do that. So this just creates a plate. But let me go back to the original plate, and after that you can define properties. I've already done that. You can assign sections. There's nothing new in any of these modules. Assembly is the same old thing. You just instance a part. Step. There are 2 steps in this: initial and step 1. So loads and boundary conditions. Let me see if we can pull those up. So the load and the boundary conditions are like this. This is a simply supported plate, which has on this edge all the displacements and the rotations that are along the edge are fixed, but rotation perpendicular to the edge is not is allowed. So that's a simply supported plate on this edge. Similarly, on this edge and the other edges, they are also rollers. So they are able to roll if the plate expands or contracts. Um, so under these loads, if you run this thing and try to plot the stresses and all that, so this is a distribution of von Mises stresses. But one thing to keep in mind when you're working with shell elements is that, for example, the section forces and the moments, they are given by SF. So these are the shear forces and the resultant forces and axial forces that I talked about. Um, Actually, I should also mention that the element that I'm using, mesh, the element that I'm using is quadrilateral, finite strain, S4 element. So this is a common type of element which is used for general purpose shell element, meaning it can handle thin and thick shells. So this is an element which is using the first order Reisner-Mindlin theory. If you were to do a small but 4-node doubly curved thin shell, so if you click on reduced integration and small strains, then the element type changes to S4R5, which is a double noded thin shell element. Now this is important because for the thin shell element, you would have to this element is using the Kirchhoff-Love plate theory. Say that again. Family of element is shell elements. So going back to job visualization, you can also see the section moments. So this is section moment in the, that is basically bending moment in the x direction, one direction. You have similarly bending moments in the two direction on both the faces. Another thing to keep in mind here for shell elements is you have different locations of these points. So let me see if we can pull that up. If we go to stresses, S11, section points are basically points through the thickness of the shell. So you can, what I'm looking here is the bottom surface. And if I apply that, this is the stresses on the S11 stresses on the bottom surface. So you can see that actually, okay, right here. So first of all, you need to also keep in mind that each shell has a material direction. So you can see here that all the material directions, the red lines, they have a positive pointing downwards. So the bottom surface actually, or the negative surface in this case, is the top surface. So that's why we have compression there. Let's go back to plot section points. So the negative face is this top surface, and on the top surface you can see that the stresses are negative, meaning compressive. If I change my surface to the positive face, that is the bottom surface of the plate, apply. Not sure. This is not okay. So on the bottom surface, you can see that the stresses are positive because they are on the bottom surface of the plate that has tension. So when you read the results from shell elements, you have to be sure about which surface of the plate you are reading the stresses from. So all right, so we'll stop here, and next Wednesday you all can go to the seminar. I'll send out an announcement for that, and we'll see if we need to meet on Friday again or not.